Hi, everybody, and welcome to another video. We're going to be talking about matrices today. And what you're going to notice about what we do today is it's going to be very similar to what you were doing last week with the solving of these systems. Basically, we're going to be using these matrices to solve them. But before we do that, let's kind of talk about what a matrix is. And no, I'm not talking about the movie The Matrix, which I know is kind of a dated reference for most of you, but math matrices. So, a matrix is a rectangular array of values in which each element is what we call the things within the matrix is a number. Okay, so in math, when we're talking about a matrix, it is a way basically to organize information in this kind of little square thing. So we have a little rectangle here, and each of these things would be elements. So 1 would be an element, 3 would be an element, 2, 7, -1, -5. And you can see over here, I say A equals. That is the name of that matrix. So this we would call this matrix A, and this would be what we're referring to, okay? Now, when we talk about matrices, you're going to see when we get a little bit later with these, is when we talk about matrices, we want to pay attention to the order of the matrix because the order of a matrix is going to change a lot about what we do with it, okay? Now, the order of a matrix we write as the row by the column. And when we tell somebody the order of a matrix, we write it as R X C, a row by column, to tell them basically what the size of our matrix is or what kind of matrix we're talking about, okay? So for this one, matrix A, this would be a 3 by 2 matrix. Okay, it's a 3 by 2. We got 3 rows, 2 columns, 3 by 2 matrix. And that's going to matter a lot for something we talk about a little bit later. Now, we can turn our systems into a matrix. In fact, we turn them into what's called an augmented matrix, and you'll see what that means in a second. Basically, what we would do is we would take all the coefficients that we have, and we just put them into the matrix into different spots. So, for example, if I wanted to turn this matrix right here, or turn this system right here into a matrix, what I would do is I would start by drawing my brackets. So I'll draw my brackets here. And then I just start putting my values in. So basically, my first row will be the first equation that I have in my system. So we'll say that this is 1, -2, 3, and then the augmented part is because for the other side of the equal sign, I'm going to put a little line here, and then I'll go ahead and put this here. Okay, put that number over here. Then you do the same thing down here. So I'll put -1, I'll put 3. If you notice, I do not have a z down here, so its coefficient would be 0. And then I'll put -4 over here. And then finally, for the last one, I'll put 2, -5, and 5. And then over here, I'll put 17. Again, just putting that over here. Now, if you notice, what's kind of cool about this is that each column is actually talking about a specific variable. So our first column is the X column, the next column would be the Y column, and the third column would be the Z column. The last column, the other part of our augmented matrix, the one that's beyond the line, would basically be the solutions to each one, the other side of the equal sign for each of our equations. So we have like equation 1, equation 2, equation 3 row, and then we have columns for X, Y, and Z. You might be saying to yourself, well, Mr. Guy, cool, why the heck would we want to write this as a matrix? Well, why would we? Because we can then do what's called the elementary row operations. Basically, we're going to do these things in order to simplify our matrix down, and it's actually going to help us solve these systems, okay? And elementary row operations are operations you can do to a matrix and keep the matrix equal. Basically, what we're going to be doing is if we do these steps, we are keeping a matrix that is equal to the other matrix. It is the same, basically, value of the other matrix that we have. Here are the things that you're allowed to do. You can interchange 2 rows. You can flip 2 rows of your matrix around. You can multiply by a row by a non-zero constant. You can multiply by 2, 3, 4, 5, whatever. And you can add a multiple of a row to another row. That should look very familiar. In fact, if you're sitting to yourself saying, I feel like I've heard of these before, it's because it's what we did last week. These are the same things as our legal moves during Gauss-Jordan elimination that we did last week. So because we are allowed to do this in the same way and it's got the same sort of steps, you should probably start to see maybe a little bit of a connection between what we did last week to what we're going to do this week. Because we are going to use a matrix to do this elimination. Basically, it's the same thing you did before, but this time we're just going to look at it in a matrix, okay? I tend to think it's a little bit easier because you have a little less stuff running around that you have to look at, a little less writing X and Y's and Z's. It's kind of all organized in this rectangle for you. Basically, you turn your system into a matrix, use our operations to create a back substitution matrix, and then go ahead and back substitute to solve. Okay, so let's go back to that example from earlier. I'm gonna kind of pause for a second, and to you guys, is gonna be like a magic burst here. But I'm gonna go ahead and turn this into a matrix, and then we'll talk about what we would do in order to solve this. All right, I'm back from the past into the future here. So we have our matrix right here. So what I'm gonna be doing is basically very similar to what we did last time. I'm gonna try to basically get rid of variables in two different spots and then kind of get rid of them somewhere else as well. So remember, this is like our X or Y and our Z column. So basically I only want one thing in this column, or three things in this row, two things in this row, one thing in this row, and then I can go ahead and solve. If I go ahead and take a look here, so it looks like up here I have a 1 in the X here. That's going to be really easy to use to get rid of stuff. So I'll go ahead and cancel out here and here. So I'm going to do row 1 plus row 2. And then down the bottom, I'm going to do -2 row 1 plus row 3. And that's what we're going to do to eliminate. So let's see what that makes for my new matrix. So let's see, our first row is going to stay the same. My next row is going to change. So I do this plus this, I get 0. -2 plus 3, I get 1. That's kind of nice. 3 plus 0, I get 3. And then 9 and -4, I get 5. And then down here, -2 and 2, I get 0. 4 and -5 will be -1. -6 and 5 will be -1. And then -18 and 17 will be -1. Man, just a whole bunch of negative ones, right? All right, so here's our new matrix. Now we'll go ahead and we'll try to get rid of this number right here because we have a 1 in this Y spot. So let's get rid of the Y here. So we're going to do row 2 plus row 3. Again, same kind of logic and same sort of method that you did without the matrices last time. Basically, it's just a new way of organizing it. Same process we did before. Still can do our back substitution and everything like that. So we'll go ahead. The first row is going to stay the same. Our second row is going to stay the same. And our third row is going to change. We're going to have 0. 1 and -1 will also be 0. Make that go away. 3 and -1 is going to be 2. And then 5 and -1 is going to be 4. Now I have where I can go ahead and do back substitution. Now this looks like just a bunch of numbers, but what I actually have here is equations that I can rewrite from this in order to solve. So this equation down here, remember, this is our Z column. So what this equation is telling me down here is that 2Z equals 4. And I can go ahead and solve that pretty easily and get that Z is 2. Now that I have that, I can plug it into this equation. So I'm going to have 1y plus 3 times 2 equals 5. And I can go ahead and solve that. And if I solve that, I'm going to get that y equals -1. And then I can plug both those into the top equation and get that 1x minus 2 times -1 plus 3 times 2 should equal 9. And if I solve that, I'm going to get that x equals, let's see, -2 times, that would be x plus 2 plus 6 equals 9. So x is going to equal 1. And so my final answer to this system would be 1, -1, and 2. And again, I did that by setting it up in this matrix and using that to keep everything organized to solve. Again, the actual process here doesn't really change. Same thing you did last week. It's just a new way of looking at it to make the information a little bit easier. Don't worry if you're like, Mr. Guy, I'm tired of doing the same thing over and over again. These matrices will give us some more power that we can use to solve these. So this is just kind of like, how do we look at what we did before in a new way to get organized so we get kind of used to using the matrices and how we want to do them, okay? So here's kind of where I'm going to leave you guys off. So for the next day or two, we're just going to kind of look at this process right here and solve a couple, setting them up with these matrices. And then I'm going to kind of show you some of the more power that matrices can give us and how actually we can use a matrix to just kind of see the answer immediately. And actually some pretty cool stuff we can do with them. But thank you for watching. Please make sure that you are okay with how to turn things into a matrix. Looking at it and being able to identify what the order of the matrix is going to be really important. And then later on, you're going to kind of see some other stuff we can do with them. But thank you for watching, and make sure that you complete the rest of the work that's listed there for the next couple of days.